Good morning. I think we can get started. My name is Ric Wheeler. I work at Red Hat, where I manage the file system and storage development teams for our kernel developers. And today I'm going to talk about persistent memory. I also want to start by just letting everybody know we are being recorded. There's a mic if people ask questions. If you don't want to run to the mic, I'll try to repeat the question. But again, keep in mind you will live forever on the internet with whatever you ask. But I do hope to have a lot of interaction, so please stop, ask questions, taunt, whatever. So we're going to start by defining what we're going to talk about today. There's actually people in the room who know a lot more about this than I do. I mean, Andy, Nisha have been working on this, Jeff Moyer on my side, and Red Hat back there. And we have quite a few of the upstream Linux file and storage developers in the room as well. You can raise your hands if you're a kernel person. So you have an opportunity to pick on people, not just me, so they can keep me honest. So we're going to start with the obvious question. What is persistent memory? Why do you care? Well, if the SSD vendors haven't made the life of file system and storage people miserable enough by working us really hard and complaining about how slow we are with latencies, persistent memory is going to make it even that much worse, right? So in a nutshell, there's a whole slew of things that we've heard about for years, right? It's been 5, 10 years talking about new types of storage technology. And there's a variety of these types of parts coming to market. But the critical things that differentiates this from a flash-based SSD you have today or a rotational storage device is, first of all, they're byte addressable, which is different for storage. We don't usually have to do that. And the other most critical thing is they don't lose state when you lose power. So a lot of the things that we worry about, anybody lost data because your write cache was on and you didn't mount your file system properly, right? You know, with barriers and stuff, maybe you don't need that for all these parts. The kind of similarities are they're a lot like DRAM, right, in some of these parts. You know, roughly the same cost as DRAM, roughly the same capacity, roughly the same performance. Now, what that means, roughly, is you're not going to have petabytes of this stuff in a single server, right? I think you'll probably still have tiers of storage. So we'll talk a little bit more about that. So again, as I said, same cost point, same capacity. And I think this means that we might have to start looking again at how do you migrate data between tiers of storage on a single server, right? You'll probably have a variety of storage types in a box, I think. And the same performance as DRAM means it's going to press any part of the stack that we use really, really hard, right? If you're driving things at DRAM speeds through the I/O stack or through a file system, it's going to be pushing us beyond where even Fusion I/O or some of the higher performance PCI Express SSD cards drive us today. So here's a great picture. This is not one I did. I tried to do this myself once. There's a very tiny attribution you can get off the web and read. I forgot who did it, but some really good developer in Germany painstakingly put the whole stack together. And if you look at the I/O stack for the kernel, you can see we actually have a lot of code between us and storage. You don't actually have to read all the boxes.
Yeah.
Yeah. Who's the?
It's Thomas Klein. It's a German reseller.
Yeah.
They're basically building white boxes.
Yeah. He did it.
They asked me for that.
He did a great job, I thought. It's a great picture. And again, you know, what we've already been struggling with, and if you look at where we put PCI Express SSD drivers, you cut out a lot of the stack today, right? The question is how much of the stack we're going to want, and how do you handle all this complexity and still drive potentially millions of IOs per second per device? So going back in history, early SSDs looked like SATA or SAS drives. That made life easy. You know, file system and storage people know how to handle 512 byte IOs. We've done that for a long, long time. And if you emulate those parts, it's pretty easy for us. You just plug it in and it works. And even better, with the original things like the parts you have in your laptops, we could actually sustain the I/O rate without really breaking a sweat. You know, there were things we had to tune and so on, but it wasn't really horrible. They all used the full stack, that whole stack that we saw, the file system and block layer, ran against SAS and SATA drives, and they used normal existing protocols, SCSI or ATA commands. The next wave of SSD devices came out, used PCI form factor cards, and some other form factors. These stressed us, and actually still, I think people in the room, Nisha from Fusion.io, others can tell you that we haven't really been able to extract all the performance that those parts can give us with most of the stack today. Because of this, there's been this new spate of custom drivers. There's NVMe Express drivers, there's proprietary drivers, there's other things. And we have been working to tune the Linux block stack. I don't know, I don't think Jens is speaking today, but Jens will be here late this afternoon, and tomorrow has been working on I/O scheduling and some queuing optimizations.
Yeah, there's a public presentation out about the latest efforts to scale the block stack. I
Yeah.
can point you guys to it.
So, yep. And Nisha had a...
That's it.
Yeah, yeah.
Oh,
Say it again.
I was just going to say that there is a public presentation out about the latest efforts to scale the block stack, so I can point you guys to it.
That'd be perfect. And she'll be speaking later this afternoon as well. So again, you know, we haven't been, in the block stack, we haven't been as well tuned to driving millions and tens of millions of I/O as our networking siblings in the kernel space, who've been doing this with 10 gig and 40 gig fabrics for a while. And more or less, historically, yeah, we haven't had to. I mean, I/O is all about high latency, high bandwidth parts. So this has been a challenge for us. So as I mentioned, you know, trying to get up to 1 million IOs per second per device with the existing stack is hard. And we're trying, and some of the work Jens and others have been doing, has been trying to leverage this into breaking down some of the bottlenecks and some of the hot paths in the stack. One thing you should do, by the way, if you are using these, even the existing class, make sure you can tune. A lot of this stuff, Martin, raise your hand. Martin worked on helping get the I/O stack support for expressing the characteristics of storage target devices. So if you go into sysblock, your device name, queue, and other places, you can poke and see what the optimal alignment, I/O sizes are. If your vendor supports those, we did a lot of work to make sure that file systems in the block layer adapt dynamically to that. You don't have to tune them, but you can actually see what they are. A lot of the things that we do today, basically, people always ask me, what do we do for Linux or SSD devices? We have rotational, I think, is the largest difference. We know whether or not the device is a spinning device. We avoid a little bit of optimizations, but we haven't really done a ton to really adapt most file systems or storage stacks to this. CFQ, though, the I/O scheduler, is probably better to use something more simple than CFQ, like a deadline scheduler or a no-op is probably the best work. And as I mentioned, there's a wealth of device driver choices in this kind of PCI Express place. NVMe is in the upstream kernel. I don't think we have shipping parts yet. I don't think there's commercially available. You do? You have a production part?
What do you mean you have production?
Well, not pre-release parts, but I don't think consumers can buy.
I said you're shipping the driver.
The driver we ship, right? But there are no cards that use the driver yet in production. Yeah. Most, I don't know, kernel developers have early access, but most users actually want drivers with hardware. Yeah. Yeah. There are a bunch of vendor-specific drivers. And you know, you will get with most distros the open source drivers in tree as part of the distro. You have to add the drivers for proprietary stuff, of course. As a Red Hat person, I'll throw in my you know, please do try to open source your drivers. It makes it easier for us as a vendor to support our mutual customers. The other thing that's kind of interesting is these parts actually stress kind of the way that we've fragmented as a community. We have people who work in different areas. The SCSI community and the SATA community are really kind of different. At the end of this week, we have something called the Linux Storage File System and Memory Management. The memory management people have added themselves to this event, where we actually get everybody in the room for 2 days, actually these same rooms, hopefully. But historically, different parts of the stack have been handled by different teams of developers. And coordination between file system, storage, and memory management people is kind of difficult, right? We don't always work on the same problems. And very specific, I think the block layer expertise itself is a very small team of developers who work in that space. File system people tend to work in their specific file system more than across a bunch of file systems. And I would actually claim that what part of the stack you work on is more important than which company you work on, right? People tend to work on a project more than they work just on a company project sometimes. So crawl, walk, run. So where are we with these new parts? I think historically what we're going to end up with is looking at how we use DRAM today. And DRAM today is used for the page cache. You can use it to hold objects that you've read and so on. And all your metadata is pretty much there. Moving away from this model, if you're going to give an application direct access to byte addressable persistent memory, it changes the way application developers work. My favorite example is trying to teach application developers to use fsync and fdatasync. I think, Jeff, you penned an article for LWN. It's been, I don't know, 10, 20, 30 years we've had these concepts. Most applications don't really use them. Anything really exotic is going to bypass most of the applications in the world. Same thing for SMP processing. Most applications aren't really multi-threaded or multi-core aware. And so as we move into new models, we're going to leave a majority of the kind of commodity applications behind. And certainly it'll be hard to adapt a lot of the existing file systems and stacks to them. So again, the traditional model, we send multiples of block I/O. We use journaling or B-tree-based mechanisms to update state. And we worry a lot about resilience because a lot of the devices have a write cache that goes away when you lose power. The on-disk state is the master. Your in-cache DRAM state is kind of the optimized state. And they might be different bits. Right? We might hold more in memory than we have on disk. So these new devices, these new persistent memory parts, actually challenge this model. So in the crawl phase, what are you going to do when you have this first batch of parts? I think the first thing we're going to have to do is probably support the majority of applications who aren't going to use new APIs. We'll probably still have, and continue to have for a long time, people who use system calls, read, write, and file system abstractions that they're familiar with. And we'll have to hide the parts effectively in our stack. Just make them as fast as possible. Ted?
Yeah, so let me challenge you on this for a little
Here,
bit.
grab a mic.
Sure.
Yeah.
Which is, let me challenge you a little bit about this, which is I agree that most application developers are very slow to use new interfaces. But many application developers use interfaces such as SQLite. And if you have user space libraries like SQLite that can directly touch and use persistent memory in a persistent in-memory heap, you eliminate vast amounts of abstraction layers than if we try to make SQLite on top of a file system, on top of a block device, work quickly on persistent memory.
Absolutely true, right? I actually agree. Good. You have another question?
Yes, but the main problem is not so much modifying things, but rather induce other companies actually recompiling their software for that new interfaces. I could mention now a large company with 3 letters, which has a software group, which is still insisting on using 32-bit applications. Because if they wouldn't, they would have to recompile.
Yeah, it's hard. And actually, I think I actually talk about this. When I say crawl, walk, run, this is kind of a marketing thing that's popular, but it actually makes a lot of sense. So the crawl phase is you get the parts, you want them to work today without people having to relink or having to wait for SQLite or anybody to recompile their apps or understand the new interfaces. This is how you start, right? When you get these first parts, yep.
So I think you're right, there's going to be a crawl phase, but I think there's actually something before this, and that is we're going to have to get used to having systems that when you reboot the system, it's not a fresh, clean slate.
That's an excellent
right?
point.
Everything is going to be sitting there just like it was when you powered it off. And
Yeah, so one of the questions is this persistent memory going to be attached to the North Bridge and being used as the main memory, or will it be something that is still being interacted with via some...
So one of the things we can't discuss here is vendor-specific parts or how people interact. I think there are publicly today you can look at battery-backed DIMMs, which have basically super cap or some kind of glue on the back instead of double-density DIMMs. You can imagine that when they get a power loss signal, they destage.
Those in the 90s.
They've been around for a while. We haven't really paid much attention to them, but to Grant's point. We assume when we reboot, your memory's clean, right? You don't always zero all your data, right? So there will be programming errors like that. But I think, actually, Grant, to your point, I think we'll still have tiers of things. And if we treat it as storage, as block storage, which is the really boring, not taking full advantage of the part crawl phase, that won't be so much as, it'll be a different problem than my file system problem.
Hey, Rick, is your mic on? Everybody else is much more amplified.
Is this better? Better? A little better up here?
I can hear you fine, but
Yeah.
I'm just wondering if it's being amplified for the rest of the room.
Should I turn it off and use the hand mic?
No, your mic is hot. It's just that you're not blowing our ears out.
Okay. But you can hear me.
Videos,
Yeah.
if these guys are swallowing it before they talk.
All right. Yeah. Okay. So again, the other thing that will happen, I mean, to Ted's point, there will be applications like SQLite, I assume the Oracles of the world, the DB2s, high-end applications, which are actually driving a huge amount of revenue, even if they're a small percentage of the install base, will be aggressive and hungry for anything that gives them extra performance, extra reliability. So it's not that in this crawl phase you won't have people using and wanting these new interfaces, but that, for the majority of people, we'll have to do both.
We don't have to only do block devices at the crawl stage. We can also do like 10% or we could get creative with in the crawl stage. So not only block device, but also like a sysfs kind of interface where you can easily access it through a bash script. But the scripter knows that this is like a persistent, fast storage, which is not block device. No, there is no block I/O at all.
So
it's like a file system within.
Totally agree, right? And actually, I think Nisha, you all have. She'll be talking later today. I don't know if you'll talk about your.
Where's the mic?
This is good exercise. Yeah. Yeah.
Yes. So what was the question? Sorry?
So Boaz was saying that you have in the crawl phase, you can also have new file systems prototyped. I think Fusion IO has one. Intel Research has just open sourced one and released one. You will have those as well, but they won't be in your standard distro, right? They won't be fully supported by Red Hat or SUSE for a while. It'll take a while for us to qualify and burn them in. So again, I think we will have to be very focused narrowly on what you do first, but at the same time, looking at this, I wouldn't call that crawl. I would call that walk, right?
Yeah, I'll be talking a little bit later about that.
Yeah. So again, I think the very first thing we need to do is, and this is kind of a shame, right? This is the boring thing, but you need a block driver to turn these really wonderful parts into something that looks boring, right? That's our first phase. I think we actually have some of this underway in different efforts. And optimally, this won't be a different block driver for every class of persistent memory parts, so that we don't have to do different things for each of them. We probably won't get away with it, but the fewer we have, the better. We have to continue to pound on the I/O path to get rid of hot paths, locking contention, get our I/O rate up. And by the way, if you have this block driver, you can just carve off a big chunk of DRAM on an existing box and pretend it's persistent. Just don't power fail test it. Right.
You can already do this with the MTD layer, and then you can put the block layer on top of that. You can do that already.
Yeah, yeah. So pointing out you can use MTD to do this. That's a great. Anything we can do to test and debug the path is really my first concern. But building on top of this, there's actually quite a few projects these days. Bcache, DM cache. You can do caching with these parts pretty easily. That's fairly invisible to applications. Pretty much everybody right away could take advantage of persistent cache. File systems, database journals, adapting SQLite. There's a lot of bang for the buck in tweaking our existing stack, our existing applications, our existing libraries to take advantage of these, reducing the heavyweight things like potentially avoiding F-syncs and flushes. And you could look at a little bit beyond crawl, how to scroll away things that are very latency sensitive, like your metadata updates or very small files. So these block drivers are being developed. Block caching is actually finally hitting upstream. I think DM cache is there, right? Went in 3.9. B cache is close.
So right now, we actually have 3 different implementations with 3 different interfaces scheduled for the next merging window. Awesome.
Hooray! Yeah. Yeah.
To be clear, DM cache went into 3.9, and B cache is staged in Jens's tree for the next window. And I'm not sure about enhanced I/O actually. Yeah. I don't think so, but I can double check.
Yeah.
I mean, the latest one is actually based on the original flash cache target.
Yeah,
and so it's still discussed, to be discussed whether it's going in or not. Alistair is supposed to meet those, was supposed to meet those folk yesterday. So is he here, Alistair? Raise your hand. What's the outcome?
It's still to be discussed.
Okay,
yeah.
so it's
I think this is a great example of the power and the curse of open source. We've been talking about collapsing SSD block level caching for like 3, 4, 5 years, and every time we talk about clashing the implementations, they double the number, right? So maybe we should talk about multiplying them this year and see if that helps. Yeah, so again, this stuff will be there, and there are vendor-specific things. Again, one of the ones mentioned was specific to STech, I believe. There's other vendors looking at this. Walk phase. And this is actually, Ted, where I look at MySQLite and looking at ext4, XFS, ButterFS, other existing file systems. What could we do to tweak our existing stack, the qualified stacks, to take advantage of these parts dynamically, right? You don't want to ship different versions of XFS or ext4, but what could we do with the existing stack to take advantage of them and squeeze as much performance out as we can out? And you could look at extending these existing file systems to expose some of the same new interfaces that we might want to do. I mean, mmap is probably not sufficient. Andy, Nisha, you have both done talks in the past. I mentioned there's a trade industry group called SNIA, Storage Networking Industry Association. It has a non-volatile memory working group, which if you're a member of SNIA, you can join and take part in a discussion about the software kind of architecture of what we're going to expose to people. And people have been talking about what APIs we want. We'd love to have feedback, right? So if you find people, raise your hand if you care. You both are there. Jeff has been monitoring for us at Red Hat. If you have ideas about how you want to use these parts from an application point of view, do let us know. But again, these existing file systems could provide the traditional block-oriented structures access and possibly expose some of these byte-oriented methods as well. And where are we with this? Things like ButterFS have some ability to dynamically adapt to low latency devices. I don't think that's really a major feature today. Where's our ButterFS people? I think that's true. I saw Zach. Look at, yeah. So I don't think ButterFS does a lot. I think it has an allocation policy that doesn't work as hard to avoid rotational latencies, but it hasn't really done a lot with SSD specifics.
So Chris has been looking at integrating some of the things that we developed at Fusion.
Right.
I don't think he's necessarily pushed them out yet.
Yeah, so the comment was that Chris Mason has been looking at, as a Fusion.io proud employee and the ButterFS architect, he has looked at this obviously, but hasn't been pushing that upstream yet. But we've been talking about this for a long time. Again, put the metadata, the trees on the SSD device and the block, the big storage on the slower tiers. We have to look at what we need to do with memory addressed interfaces, mmap and friends, madvise, whatever. Are they salvageable? People are kind of skeptical, right? But maybe it'll take us part of the way there. And you need to educate the developers about how to use these things. And that's actually one of the most painful things. Whatever we do, it takes forever to teach developers, application developers, how to use the new interfaces correctly. That's my experience. Willie, so go ahead. Mike back that way.
Thanks. Yeah. So what that was Matthew Wilcox tried to get a conversation going on the Linux kernel mailing list about an in-kernel persistent memory API. And so we just a couple days ago, I haven't sent out much mail about it, but we just open sourced the implementation of that. Yeah. The file system that basically exposes that. But we're still kind of looking for comments on what that in-kernel API should really look like. Should you be opening things by name, or do people really care to do that? Instead, do they care to just go get unnamed volumes of persistent memory? And so we're trying to really go down both roads at the same time, because I think there are kind of use cases for both. So it is progressing. We're maybe not as vocal about it as we should be.
Yeah, and I do think, I mean, it's really interesting. So one of the comments I got when I proposed this talk and this for our LSF agenda back from James was the traditional thing, is that people have been threatening us with these parts for like 10 years. They are coming now, right? So we can't ignore them, right? So this is the time to talk.
Yeah, I mean, my comment when I first heard about this is they've been 2 years out for the last decade. So, credibility sometimes gets a little bit strained when that happens. One thing that's not clear, and I think it's going to make a huge difference as far as the getting developers educated and willing to use it, is whether these devices are in the hundreds of dollars, thousands of dollars, tens of thousands of dollars, or hundreds of thousands of dollars. Because I suspect traditionally one of the reasons why we've been so slow with adoption of, for example, making our stack work well on really high-end PCIe attached flash is that for many developers they are effectively made out of unobtainium. And just the reality, right? They're expensive parts, they're designed for high-end servers, and that's very, very different from if I can get a $200 mSATA device that I can drop in my laptop. You will get many more developers, both at the kernel level and at the MySQL application level, developing. And I don't know that anyone can comment on price points, but it's going to be a huge factor.
The guidance I've been given from partners who shall remain anonymous is think of them as the same cost point as DRAM, right? And if you look at it that way, give or take, whatever. I mean, everybody's going to have a different price point and a different capacity, but roughly the same size, capacity, price point as DRAM. And that gives us actually a lot of usable stuff, but it means you're not going to have petabytes of this in a box. It's not going to be petabytes. And that's why I go back and saying I think we're going to still have tiering of these things. You might have mixes of DRAM and persistent DRAM. You might have SSDs on PCI, and you might have rotational storage as well. So I think, Ted, it will be actually attainable, and it'll be fairly common, I believe. Right? You need a mic. Yeah.
So I sit in Linux conferences and the developers kind of talking about, oh, we are kind of still waiting for these kind of devices to become more mature. Yeah. And I also sit in other conferences where the hardware developers are looking at, oh, we need operating system support for this, otherwise it's not going to fly.
Yeah.
And then there are customers who are saying, hey, I don't have support in hardware, I don't have support in software. Where do I go? And then somewhere along the way, some companies do something disruptively, and then they just come and write applications and make it really fast, and everyone starts looking at it, and that's when the tipping point is. I don't know when the tipping point is, but it depends on who's taking the lead right now.
You guys, these are great segues. So I'll get into I'm going to skip ahead a little bit, but one of the things we're doing, the run phase. This is when you actually look at how you'd want to use these parts natively to their full capacity, their full availability. And kind of, what APIs would you want to give to applications developers? What APIs do we want from the parts up to the kernel, right? And that's kind of where we're at that phase now. I think SNIA is the only public forum today for that. Is that true? Is there others?
Well, there's always the Linux kernel mailing list. I mean,
LKML is a great place to spend endless days reading email.
Right.
Yeah.
And it's a much more public place.
And it's very
much
more public.
Yeah, and by the way, we will be doing both, right? But some of the stuff, Red Hat's not a member of SNIA, but if we do become a member, we'll be taking part in that and still trying to drive an open source discussion. I mean, there's no value if you can't have an open discussion. But I do think that these new APIs are part of the run phase, because it takes a while for us to adopt a shipping enterprise version of Linux that whichever vendor you have gets to your customers. And it'll take even longer to get the applications tuned to to that shipping version of Linux. Well, so the question is, if it's the same price point as DRAM and same capacity, you could have it just in the box as DRAM, potentially. It might have different performance than you're expecting, it's slightly different, but the file system wouldn't live on it, right? We still have to teach a file system how to do recovery, because we have this nice clean transaction where you send a write down and it's acknowledged. In a file system, we know it's, we do synchronization methods based on journaling and stuff. There's stuff you have to do even with the DRAM. So we'd have to treat it as a block device, I think. Your mic back.
There's actually another issue to that you might want or you will want to zero memory occasionally. If your system crashes, you really, really, really want to wipe out the thing to know that you're starting off from scratch. If you're using persistent memory, your memory won't be wiped out. So you start with exactly the same system you left off with, and it hit the same crash. Not what you want.
Yeah, there's a question in the back. Comment? Yeah.
Actually, there's been an approach to this problem that has been run for 10 years or so in the mainframe area, which is called execute in place.
Yes.
And there are patches for well, they are not patches. This has been merged. Ted, you know all about it. And essentially, you can take a block device that also happens to be memory, and you can treat it as a block device. You can have a file system on it, but you can memory map the files on the file system, and they do not get copied in the page cache. They stay as memory, and you just tweak the TLBs and access them directly.
Yeah.
So that may actually be
a shortcut
the best
to
approach.
Yeah.
At least I wouldn't know of anything better right now.
Yeah. So.
It's also possible that whilst the performance of DRAM and performance of persistent memory is the same, the lifetime isn't. So the persistent RAM may not last anywhere near as long as the DRAM if you just write to it in the same way you would predict DRAM.
Yeah.
Right. The point is that the physical, the price performance may be the same, but the physical characteristics won't be. We already know from, for instance, flash memory that it has issues with load wearing over time. Things like that that require you to take into account, the way that you lay out your data, that sort of thing.
Yeah, these are all good points, right? And again, a lot of this will be very part-specific, technology-specific. What kind of oddities you have. Hopefully we'll hide that under a driver or under BIOS or something, right? So again, I mentioned before SNIA. There's a pointer to the working group here. There are several file systems. Intel Research has put one out. You said it's an ext4, the execute in place support? Okay, so we can try things like that. I think, Nisha, you all have a project you'll talk about later today. But I do feel that this is going to be potentially as painful as teaching people about 64-bit or multi-threading or even fsync. Right? It'll take us a while. So this is kind of my favorite talk, and this actually goes back to, how do you get stuff into Linux? So as Shyam pointed out, a lot of hardware vendors think of us as a mysterious community. It's as if they can't read email or come to conferences, right? But it is pretty hard, right? Because Linux isn't just the kernel. I mean, as kernel people, we actually normally think we're done when we're done with our little specific kernel module. But there's a whole ecosystem on top of it. There's hundreds of projects that go into an enterprise distro, each with their own community, their own rules. Sometimes we like each other, sometimes we don't, right? Sometimes, the file system people change something, and MySQL people don't take advantage of it correctly, or vice versa. And so what it means is when you get really new technologies in, it can be a multi-year road. A good example, PNFS, parallel NFS, has been in development for 10 years. 10 years.
At least 10 years.
You turned off your mic.
Yeah, at least 10 years.
At least 10 years. 10 years, and I think we can claim that first enterprise support for PNFS went out this past year. Yeah.
Only the client.
Only the client side, no server. Yeah. Yeah. So performance monitoring, 6 years. It takes us forever to get this stuff into customers' hands. So, you know, and the other thing is that's really frustrating to hardware vendors working with Linux. You can't come to just Rick, the Red Hat guy, or to Hannes at SUSE and say, hey, can you make it work for every version of Linux, including Android in the universe? It doesn't work, right? Unfortunately, you have to work with the upstream communities, or you have to work with everybody. Yeah, and again, it's not just the kernel, right? There are things that you know, break in user space. Right? We have a lot of work in user space. So, how do these things come about, right? Some of it does happen initially, either because of some research group, some standards committee. They'll propose a standard. I think the SNIA probably will come up with some proposals. Whether or not they're adopted by Linux or not, or adopted broadly by industry, I think they have a fairly good chance of being adopted by the hardware vendors. I think a fair amount of the vendor community is there. The way we like to get patches into Linux is propose code, right? Talking is cheap. If you have code that shows how the driver works, that's wonderful. If you have a passion for your specific application, test, feedback, advocate for inclusion, right? If Tejan posts a patch and nobody in the universe actually uses it or cares about it, it's... Yeah. Yeah. And eventually, you know, it goes through a community distribution. When you integrate all the pieces together, we did this in Fedora for PNFS, for example. We put all the weird PNFS bits together, including the kernel in Fedora. And after it bakes for a while, someone will be brave enough to put it into an enterprise distribution that some customer would pay you for. Right? Is there a comment? No? Okay. Yep. Yeah, and this is actually John. This is John's work, about to be updated. But again, just showing it is actually distributed over a ton of companies, right? This is just the top 10 for 3.8, if I typed in these all in by hand correctly. You know, it takes a lot of people to make these changes. Here's some of the people. Actually, some of them are actually in the room. I like to show this. This is the people who work in storage and file system technology. It's a fairly small community. About 90 of us will be here this week talking about kernel stuff. There are more people, of course, who work on this on a regular basis. And I think I'll wrap up here. Some pointers. I don't get paid by John Corbett to flog LWN subscriptions, but John and his crew do a great job keeping you up to date on the kernel and what we're doing. If you're interested in this work, we will be discussing it on all the various lists, Linux SCSI, the file system development list, other particular projects. There is this NIA non-volatile working group, TWIG. It's a cute kind of name, a TWIG. But you do have to be a member of SNIA to take part, I believe. Right? And there are workshops like this and Linux Foundation workshops. So with that, I'm going to wrap up, actually even earlier than Hannes, but we can talk about questions. Yep. Yep.
So as someone who has been working on block layer for a while, so my frustration with non-volatile storage is that there's nothing concrete, right? I mean, I don't know what to target on. People tell me about like crazy things, but there's no product that I can use. I'm not sure. I mean, so there's fairly high-end devices which reach the things which are really, you know, really nice, really crazy stuff, you know, byte addressable, memory mapped. You cannot even tell it's persistent or not because it's so fast.
Right.
But they're all really high-end, right? They're like
I think the world will change, right? And again, you know, so what's going to happen with this? And the point is that, again, you don't have access to real working hardware that lets you test.
So I think I mean, as a developer, what I need is that I need to see the direction that it's actually headed. I mean, is it going to be, you know, really, can we wear it out? I mean, how is lifetime going to be? How is it the latency behavior going to be?
Right.
How is the, you know, what are the interfaces which are proposed? I mean, I mean, currently there's nothing concrete about it. People are just talking about it.
It's all under NDA.
Yeah. I mean, so I mean, I cannot make any engineering decision based on.
Some people are going to be lucky enough to have their brain split in half, right? So you're going to have the NDA part of your brain, which will know about this. if you work for Red Hat or for SUSE or Oracle or Fusion IO. And you're going to have your public brain, which is going to have to try to promote something generic without revealing corporate secrets. Right? This is what's going to happen. Right? But that's going to happen. I think that multiple sources are going to give us parts. And we will have parts. So they will be real. You will have them, and we'll have to figure out how to promote things that we can't talk about.
Yeah, well,
like,
I mean,
like with this talk.
Yeah, we'll have to figure out that. As just about execute in place, just as a factoid, it only works, the only file system out of the 70 file systems that we have in Linux for which execute in place works is ext2.
ext2.
And that's because the only block device today that supports execute in place is the S390 DASD, and none of the ext3 or ext4 developers have S390s in our basement. So, you know, again, it's one of those things. I can't do anything with execute in place until I have hardware. It's just not possible.
May I point out that we do support XFS on S390 and Fedora. Yeah. Yeah.
Actually, this is not true. Because it's a generic file system. There is no, the execute in place does not have any.
No, it does. I just checked the code.
Exactly. You can't just use RAMFS and just. I mean, sure, it won't be persistent, but you can. That nothing which hinders you to indeed put it on RAMFS or something. Yeah. That does work. Johan, correct me if I'm saying something stupid, but that's not right. Regarding Tijon, I fully agree with you. I'm trying to get my hands on one of the SuperCAP-backed NVRAMs for 2 years. And as it turns out, the devices are there. You can buy them. Not a problem at all. And they're not even that expensive. That costs you about 50 euros or something.
Yeah.
So, but you can only plug it into your system if you have BIOS support for that thing. Because, as I said, the BIOS will wipe the entire memory, which is not what you want for a persistent device.
So I do think,
So you do need BIOS support for it, which means you have to talk to the hardware vendor. Hey, would you mind modifying the BIOS for me? Yeah, sure, we will.
Well, there's two phases. There are two phases, right? So for most of us, if you don't focus on the persistent element of it itself, how you recover after a power outage, you can debug the performance aspects of the stack and the execute in place on just regular DRAM and pretend it's, you know,
but we don't know.
because you know, you believe, Rick, that you're going to have these real parts. Yeah.
They've been telling us this for 10 years.
Yeah. Yeah.
So back to block devices.
Yeah.
So I can imagine how this is going to work for PCI devices. We just map the persistent RAM into the PCI address space at init and take off and do things with it, and it's all together in one device and lovely. So, but what what about SATA devices? How are we going to use this stuff with SATA?
It won't be SATA. I mean, so it won't be SATA at all.
SATA is becoming PCI Express too. So
yeah.
So forget it and just stick with.
Yeah. So again, if you have a persistent memory technology behind a SATA bus or a SAS bus or a fiber channel bus, it looks like a fiber channel SAS SATA drive.
If it weren't, you wouldn't want to use the protocol.
You wouldn't. Yeah. It's just going to be block oriented.
Okay. So so the answer is it'll never
happen.
happen.
It'll be somewhere else in the system, probably. I mean, these technologies will be. They'll look like DRAM or they'll look like something else in your address space.
Yeah, if it's behind SATA or SAS, it's already there. You have back off.
Yeah. I mean, Texas Memory Systems, I think, was a vendor who shipped, you know, a case of violin, ships a rack of memory with big batteries or something. Yeah, so you have those. Please?
So what do you do about redundancy?
Write it twice.
So how many layers are we going to put in?
Yeah. No, again, this is...
You're going to have to do something between the application and the actual devices if you want to have redundancy and failure protection.
Well, this goes into...
and stuff like that, right?
This is a great question, right? So again, Hannes talked about software RAID. You could RAID these parts in software, but then you pull in more of your stack.
Device, though.
Some of your parts... Some of your parts...
How do you do byte addressable RAID?
Yeah.
So, a popular topic about 3 years ago, or 2 or 3 years ago, was the file systems, the file storage, no, object-oriented storage?
Yep.
That Seagate was doing. OSD. So who's doing that now? Maybe 5 years ago.
Panasys. Panasys does OSD.
What do you want me to say? I mean, no, I said that we have OSD targets of sorts, of all kind of sorts.
Well,
and
so how well would it apply to this problem?
Totally different. So OSD, I mean, there's, first of all, OSDs, there are different OSDs. This is way off topic, but this is fun anyway. So there's OSDs with a SCSI T10 OSD spec. I mean, there is a SCSI object standard which is different. It's just a block device standard that has object IDs instead of LUNs. And you don't have to worry about LUNs. You don't have to worry about mount points for your filers or IP addresses. You need an object ID. There are object IDs implemented in user space. There was, again, through SNIA, I think a fairly dead standard called ZAM, which was an object content addressable storage thing. There are other objects more in the archival space where you have some kind of crypto hash to ID your object. Panasys is more SCSI T10 object, right?
SCSI T10, yeah.
Yeah, so again, object is kind of orthogonal. Who? Dan, you have an object?
A page.
A page, yeah. A page is an object. Yeah. So again, there are things you could do, right? I mean, it's, you know, it actually is one of the debates that I think they'll have in the SNIA twig is what kind of ID do you need for this to get applications to use you? Yeah. Yeah.
I want to know how do you reference and share objects, right? And share data.
Oh, yeah. Still doesn't answer the redundancy problem.
So just to be clear about what the twig is doing, it's stopping short of defining an API because we think that the last thing the Linux community would respond well to is a standards organization trying to push an API on them, right? So what we're trying to do instead is come up with a common set of operations and trying to both influence the vendors of the devices and also the operating system vendors, Linux community being one of those, right? And so the two questions that just came up, one about replication is one of the hardest ones for persistent memory because there is no interception point. Right, the whole point of persistent memory is that a process gets direct load store access to this persistence. So there's no interception point. So what do you do if you want to make that replicated? And we have some proposals, and they're rough, but they basically, they leverage the fact that an application to really leverage persistent memory is going to be changed, right? There's not, you don't take persistent memory transparently and suddenly make an application go, wow, it's so much faster or something. It's not going to happen, right? So since the application already has to react to the existence of persistent memory, you have an opportunity there to give the application an API for replication. So I don't think transparent replication is something that software is going to solve.
And I wasn't entirely being facetious when I said write it twice, right? I mean, I had a colleague at Thinking Machines, Brewster Kale, I think it was, who at...
So you just asked why not?
Yeah, why not?
Yeah, why not? And that's because...
When we do that, that's how replication does not have to be instantaneous. There's lots of gray area there, right?
Well, if it's not instantaneous, how do you do failure recovery?
No, so this is a great comment. So the comment was replication doesn't have to be instantaneous. So what about the eventually consistent style replication? I think that's a great idea.
Yeah.
Certainly it's a possibility, right? And I think that there is a class of problems, especially in big data, for that eventually consistent model. But for typical write caches of I can't lose this data with a single point of failure, that isn't sufficient. And so either there's a solution that will emerge where the hardware handles the replication, or there's an API where the software writes it twice, basically.
Yeah. And I think write it twice is, if the cost point is sufficient, I mean, you need double capacity or whatever, you would write it twice effectively.
And then the second comment was about objects, and why isn't persistent memory just this big giant distributed object store? And I really want to encourage that kind of playing around and evolution, but there are applications waiting, just like a lot of you guys, waiting to use persistent memory or ready to use persistent memory today that don't really grok that kind of an distributed object store just yet. So I think we want to start with the axiomatic interfaces where we get the persistent memory out there and then build things like distributed object stores on top of that over time. So
Jim has been waiting patiently for a
there you
comment
go.
in the back there.
Yeah, this is deja vu all over again. My first Unix machine was a PDP 1170 that was built before DEC went into this new memory technology called CMOS. I could unplug my 1170. I could just reach over the wall, give it a twist, pull her out, and plug it back in, and it would just pick up mid-ed session, okay, and just keep right on trucking. And
it was a big plug. Yeah.
Actually, that machine, it was 5 30-amp plugs, and I can emulate it on my Raspberry Pi, so that tells me how old I am.
Space shuttles still use core memory.
They do. Well, this is the first I have actually heard of this NV Express, and from what I'm hearing
just to be clear, NVMe Express is just a driver for PCI Express form factor SSDs, which is different than non-volatile memory. It's block. It's block. So it's confusing. The name NVMe and NVM.
Well, what's strange about this is I had a discussion with one of Boaz and I worked for the same nefarious outfit, and I was talking with one of my colleagues, and we have an issue of we want to harden our file system for when PG&E pulls the plug, which seems to be every other day these days. And I said, well, let's come up with a way of persistent memory. Now, if this whole spec is to deal with brain-damaged BIOS programmers that say we have to blow all of memory because it's DRAM and we have to resync all of, and get the RAS-CAS going again and all that junk. That's fine if it maps to the address space so that I can map this thing and do what I'm interested in is a reliable 64-bit write that I can put a memory barrier behind it before I do the pthread unlock to get to details. Then I'm a happy camper because then we can deal with.
Sounds like you need, for that level of detail, you should go join the twig.
Yeah,
I think.
But
yeah,
what this is core memory. Just a hell of a lot of it, and it does what core memory does. Because I could turn off my PDP-11 for a year, turn it back on.
Yeah, I mean, it's a absolutely fair comment. I mean, core memory had a lot of these characteristics, but not at the same cost point and capacity. Right. So
yeah. Well, my PI cost $35. That thing cost me $400,000.
Right. Yeah, and I think actually the cost point and the economics and the size is actually a game-changing. One of the game changers of the technology. You could make persistent memory years ago, decades ago, just not efficiently and not at scale.
Yeah,
that's going to change.
We did a bunch of those things, and there were some fairly simple things that we did because your registers got stored to core before the power drain doesn't necessarily mean that your kernel was in any good shape. So there's. Right. I'm a little concerned if we wire things up with magic device drivers and stuff like that, where it's memory that doesn't go away, but it's memory you also can't trust until you looked at it. And me personally, I just like to be able to put it in the address space and then have somebody look at it. Do these bits make sense, or did the high cap die?
Yeah, and that's, in some ways, that's a little bit of a different problem than the file system persistent store problem. There's a running program image problem, which is, I think, different than the focus of the SNIA NVM twig. Is that true, Andy?
Well, that was the subject of our conversation last week, is can I trust what is essentially my metadata cache and my version of the Dcache? Is it really any good? And there's old tricks to do that.
Yeah, so the point of the twig is very much at the application programming level.
Okay.
And so the answer to things like can I trust the data and things like that, that's in introducing the appropriate interfaces for discovering errors. And
yes.
That stuff's really not very well thought out for memory because applications tend to not deal with things like uncorrectable errors in memory. That's usually the OS that deals with that. And yet with persistent memory, that's got to change, right? We have to change it so the application really can do something reasonable and get reasonable information about things like well, gosh, you thought this was persistent, but now it's gone.
Right.
Just like it does with storage today.
Right.
The CPU has to return EIO. Yeah, more or less. Oh, that's a great comment. We should talk.
Yeah. So Boaz is asking, what is the failure characteristic?
So the question is, what is the failure characteristic if it looks like DRAM?
No, I'm saying, what is the failure characteristics of these devices? Because if it's like DRAM, then we don't do replication like disks.
That's right. Yeah.
Because the disks the problem with disk is that the failure is random. Is a Russian roulette.
So the question is, what's the failure mode of persistent memory?
DRAM is not. DRAM is
yeah.
Please shut up until you have the mic.
Okay. I'm saying, what is the failure characteristics of this thing? Because replication is a statistical solution. And so if the failure is different than a disk, then it would be very, very stupid to do RAID 5 or replication like we know it. We need to understand. And if it's DRAM, usually it's when you do the DRAM test and you have the ECCs, then the ECCs are always checked, right?
So, Boaz, I
and
think
you're frozen.
I think we can't get into. I mean, I'm going to guess that none of the vendors here will say this on camera.
Okay.
In an audience, but the parts will have different characteristics. I do think that almost any vendor would be happy to sell you twice as much and have you write it twice, right? Not to RAID, right? But I think actually that's not going to be uncommon. I think replication might be.
Yeah, but Boaz has the key point there.
Yeah.
Is that DRAM, when we get down into the electrons, DRAM is got the same kinds of problems. And we solve that with ECC, and you get a machine check that says 64 bits you did a fetch on is crud.
Yeah.
Okay, and so that's where I was commenting earlier. Is this isn't a RAID 5 shelf that we've got to do the kind of magic that Boaz is talking about. If it's memory and I've got it ECC'd however many bits I need, and it'll be alive for a year, let's not get too complicated.
Yeah. There was a question over here. Yeah.
More of a comment.
Comment?
And I'm probably going to betray some massive ignorance here because I'm not a file system or a storage guy at heart. But when you're talking about the writing it twice and having twice as much available to do that, and just in general the concept of having this around as anything other than a cache on the deeper level storage. To me, thinking of it as anything else makes me very nervous, just because I'm thinking of the byte addressability. Current CPUs, as far as I know, architecturally, physical address space is up there. It shouldn't be a problem. Implementation, there's very few that go above 44 bits now. Most of them are around 40, quite a few are around 36. If this is also DRAM, that's a little better. If it's sharing with DRAM, you're eating a lot of space right up front. But I mean, you're thinking about it on a typical 36-bit physical address space laptop that gives you 64 gigs, and you've got to share that with PCIe. You've got to share that with everything else you've got in there. There's obviously going to be something else in there for your permanent, really permanent storage, or people are going to get used to writing almost nothing.
These are all excellent questions. Yeah.
Yeah. Well, and that's the thing. You can do that kind of tricks, but I mean that's more complication either in the kernel level to get it right, or God help you in the firmware level if you're trying to hide it there. But yeah, right. Or it's something else for the application developers to have to worry about even more if you choose to expose it up to that level. So it's just it's something else to keep in mind and think about.
Well, and I think this is going to be the long-term challenge here, which is even if we have some developers under NDA who can operate in split brain mode, having design discussions in the open community on the open mailing lists where we have to make these sorts of trade-offs, right? And there are very fundamental characteristics mean that it's going to be very, very difficult, right? I mean, and I suspect the only way we will make forward progress is if one of the vendors is brave enough or is close enough to ship date that they are willing to publicly disclose what the characteristics of their technology is. And then we will start implementing for that technology, which will force the other vendors who may have slightly different characteristics to pipe up and say, no, wait, ours works this way.
I think
but
you will
until
get-
we do that, split brain is going to be hard, because what's going to happen is those of us under NDA will have to say, trust us.
Well,
This is okay, we're doing it this way, but you know, I can't
two
tell you
comments,
why.
right? One is I
You
think
know?
you will have some vendors who are more open with what they're doing, and you'll have parts that'll be available, you know, and you don't need to know every last nit and detail of an implementation to know the characteristics.
The problem with split brain operation is that you cannot build consensus, and without building consensus, you cannot make fundamental changes. And you're asking for, you guys are asking for a lot of fundamental changes without giving anything concrete. So there's no consensus, and there's will be no progress.
I think the vendors understand this, and you will have parts that you can buy commercially today. I mean, like honest, tomorrow. You have parts you can buy immediately, basically, that'll let you at small scale, not at tens of terabytes, but at small scale, do these battery-backed DIMMs to test if you want to today. I mean, I think those are commercially available.
And an issue of BIOS not supporting it.
You have to find the right motherboard or vendor, and I think the vendor could. I can't name the people today, but we can work to.
Hundreds of dollars. It's hundreds of dollars plus $1,000 for a magic motherboard, right? I mean,
But that's not hard, Ted. I mean, honestly, Ted. I mean, let me put it this way: for $2,000, there are few of us employed by commercial companies who couldn't spend $2,000 on a test box. Honestly,
So one comment I'd like to make is that the NVMe Express standard, has currently standardized the block part of the protocol, but a lot of the queuing interfaces and so on are designed so that they would support more than a block level interface to the storage. And as far as NVMe Express devices are concerned, they're going to be out soon, and at relatively low price points. And the NVMe interface was not designed specifically with flash in mind. There are many competing technologies for the post-flash world with many different characteristics. So one of the driving factors behind NVMe Express was to make the interface as agnostic to what the underlying technology is as possible. So it'll be possible for us very soon with commodity parts to start working with devices, and the performance and the characteristics may change, but the interfaces may not.
which is great. And again, some of this stuff is just obvious, right? So even if you have these small capacity parts that are DRAM speed, you can expose weaknesses in the stack, right? You can expose performance bottlenecks.
It's not only about the development itself, but if it's going to be mainstream.
It'll be mainstream.
If it's not going to be mainstream, why would we invest?
No, it is. I mean, I think that there are enough people who are under NDA can tell you that it's mainstream because we're getting hit by multiple vendors.
I heard it a lot, but I haven't seen anything.
Yeah, it'll be mainstream. And I'll just say, we're actually past the hour, and we're eating into your coffee break. So I'm going to turn off the mics, but we can still stay here and talk for another half an hour before the next speaker. So one last question from Daniel.
Okay. Short question, maybe.
Yeah.
Why is this more complicated than just mapping the persistent memory at device init time and providing a discovery, some kind of discovery for that memory?
Yeah. So you can do that, right? But then what do you put on top of it? What stack do you run on top of it? And what applications?
That's my problem.
Yeah.
That's all I want personally, and I know exactly what to do with this memory.
Maybe this is a dumb question, but is there any way we could fake it with QEMU so I could pretend to have a fast sports car and maybe start playing with this today instead of waiting for hardware to show up?
Sure.
Maybe.
Currently there's exactly two users of execute in place. One is the mainframe Metadata, and one is NOR flash, and that is pretty much limited to the kernel image itself. But you can take an empty DRAM device, so you can just take some part of your system RAM, boot with mem equals 1 gig or whatever and use the rest as your MTD device. You can put a block device on top of that. You can mount it as a file system, and the execute in place support for MTD is currently limited to NOR flash, so you will have to do some hacking yourself. But if you're willing to invest time, you can do it right now.
Yeah, but I think you might not have the performance you need. So again, one of the challenges is going to be driving enough the stack to actually expose where we're not working at the level we need to be. And I would just use DRAM. Use DRAM behind some kind of RAM device, RAM disk-like thing. Okay. Well, thank you very much. Let's just go.